Now we turn to the operations themselves. All three algorithms in this chapter share one mechanism. Let's line them up side by side. Dijkstra repeatedly finalizes the closest unfinalized vertex, then relaxes its edges. It reuses the Chapter 12 min-heap priority queue. Prim repeatedly pulls the cheapest crossing edge into the tree. It reuses the same min-heap priority queue to hold its frontier. Kahn sort repeatedly removes a vertex with 0 in degree. It uses a plain array queue plus the in-degree array. All three are greedy. At every step they take the best option available right now and never revisit that choice. The invariants from earlier are exactly what makes that greediness safe. Relaxation is the main mechanism of this whole chapter. Let's see it at 3 levels of detail, all in one table. First, the idea. If going through U gives a shorter path to V than we knew, we act. In pseudocode, if dist at U plus the weight of edge UV is less than dist at V, the C line is the same test. If dist at U plus W is less than dist at V. Then we update. Dist at V becomes dist at U plus the weight of edge UV. The C line is the same assignment. Finally, we tell the priority queue about the improved distance. In pseudocode, we insert into Q the vertex V with its new distance. In C, we push the new distance and vertex. Relaxation just means updating your best-known arrival time as soon as you find a faster road in. Every shortest path algorithm here is built from this one step, used on different edges in different orders. Dijkstra needs to lower a vertex's priority in the heap when a shorter distance appears. Instead of hunting for that entry inside the heap array, the classic decrease key move, this course uses a simpler way that is just as correct. First, push a duplicate. Every time a distance improves, push a fresh distance and vertex entry into the heap. Second, on pop, check if it is old. If the pop distance is larger than the vertex's current best distance, that entry is out of date, so skip it. Third, no decrease key is ever implemented. We never reach into the heap to edit an entry in place. So a vertex may sit in the heap several times, with different distances. Only the smallest copy is ever acted on. Every later, larger copy is simply skipped when it is popped. And the cost still holds at big O of V plus E, times log V. Each relaxation pushes at most one extra entry, so the heap may hold up to big O of E entries. That makes each heap operation big O of log E, which is big O of log V for a simple graph. This is Dijkstra in CLRS style 0-indexed. Q is the min-heap priority queue ordered by distance. We set every distance to infinity, then set dist at S to 0 and push the source. Then, while the queue is not empty, we extract the minimum, the pair with the smallest distance. Now look at the loop body. If the popped distance D is bigger than dist at U, this is an old duplicate, so we continue and skip it. Otherwise, for each edge UV with weight W, we relax. If dist at U plus W is less than dist at V, we update dist at V and push the new pair. There is no decrease key. One hard requirement, and it is the biggest limitation of this algorithm. Dijkstra needs non-negative edge weights. Every weight W must be 0 or more. A negative edge can beat a distance that has already been popped from the queue. Because this version keeps no settled set, it repushes and processes that vertex again. The greedy guarantee and the speed bound both break, and a reachable negative cycle never ends. There is no error and no crash to warn you. One more note on sentinels. There is no nil here. Every distance starts at the infinity sentinel and only ever decreases. In C, that infinity is int max, a documented sentinel value, not a pointer. Before the trace runs, let's set the scene. The source S is just settled. Dist at S is 0, dist at T is 10, dist at Y is 5, and everything else is infinity. First question: which vertex does Dijkstra settle next? Not which one was discovered first, but which one does it settle? Second question: when you relax that vertex's edges, which distances change? Take a moment and commit to an answer out loud before we reveal it. It settles YY has the smallest tentative distance, 5, which is smaller than T's 10. Relaxing Y's edges then improves T to 5 plus 3, 8. It sets X to 5 plus 9, 14. And it sets Z to 5 plus 2, 7. The greedy rule is always, settle the closest unsettled vertex next. Let's trace Dijkstra one pop at a time. The source is S. Watch the colors. Green means a vertex is finalized. Teal means it is tentative, still waiting in the queue. Red marks the vertex we are settling this step. Cobalt means we have not reached it yet. Right now S is red, the source we settle first. On the right is our table. We build it like a teacher at the board. Each pop adds one new row and the old rows stay, so we can always look up and see what changed. The first row is the start. Dist at S is 0, and every other distance is infinity. The queue holds one pair, distance 0 with vertex S, so we pop S first. We pop S and finalize it, so S turns green. Now we add a new row for S. Now we relax the edges going out of S. Relaxing an edge just means lowering a distance when a shorter path shows up. The edge S to T has weight 10, so in the new row, dist at T becomes 10. The edge S to Y has weight 5, so dist at Y becomes 5. Compare this row to the row above. T went from infinity to 10, and Y went from infinity to 5. Both are teal now, which means tentative. The smallest tentative distance is Y at 5, so we pop Y and finalize it. Y turns green and we add the Y row. Now we relax Y's edges. For T, dist at Y plus the weight of edge Y to T is 5 plus 3, which is 8. 8 beats the old 10, so in this row dist at T drops from 10 to 8. For X, 5 plus 9 is 14. That is X's first real distance. In the row above it was still infinity, and now it is 14. For Z, 5 plus 2 is 7. So Z drops from infinity to 7. In this new row, T is 8, X is 14, and Z is 7. The smallest tentative distance now is Z at 7. We pop Z and finalize it. Z turns green and we add the Z row. We relax Z's edge to X7 plus 6 is 13, which beats 14, so dist at X drops from 14 to 13. That is the only change in this row. Z's other edge goes back to S, but S is already finalized, so nothing changes there. The smallest tentative distance now is T at 8. We pop T and finalize it. T turns green and we add the T row. We relax T's edge to X8 plus 1 is 9, which beats 13, so dist at X drops from 13 to 9. That is the only change in this row. The edge T to Y would give 10, but Y is 5 already, so Y does not change. Only X is left. We pop X and finalize it. Now every vertex is green. This last row improves nothing, so it is our final answer. Read it across. S is 0, T is 8, X is 9, Y is 5, and Z is 7. This matches the book's answer exactly. Here is a quick check on that trace. Start from the state right after S and Y are finalized. Do one relaxation round starting at Z, which distances change, and to what? Pause and work it out. Let us work it out. Z's edges are Z to X with weight 6 and Z to S with weight 7. Dist at Z plus 6 is 13, which is less than dist at X 14, so X updates to 13. Dist at Z plus 7 is 14, but S is already finalized at 0, so there is no update there. The trace showed each real pop, one frame at a time, but the priority queue actually runs extractment 8 times, not 5. This table shows every single pop, same graph, same numbers, including the old duplicates the step notes warned about. Pop 1 takes the pair distance 0. Vertex S we finalize S at 0. Relaxing S pushes the pair 10 T and the pair 5 Y into the queue. Pop 2 takes 5 Y the smallest. We finalize Y at 5. Relaxing Y pushes a better 8 T plus 14 X and 7. Z notice the old 10 T is still sitting in the queue. Pop 3 takes 7. Z we finalize Z at 7. Relaxing Z pushes 13 X. Pop 4 takes a T we finalize T at 8. Relaxing T pushes 9X, which beats every earlier copy of X. Pop 5 takes the pair 9X. We finalize X at 9. That is the last real vertex to settle. Pop 6 takes the old pair 10, T, but T is already finalized at 8. Since 10 is bigger than 8, the check if D is greater than dist at U fires and we skip this entry. It does no work at all. Pop 7 takes 13, X, another old copy, skip the same way. And Pop 8 takes 14, X, the oldest copy of all, skipped, and now the queue is empty. 8 pops for 5 vertices. Let us say exactly where those stale entries came from. Pop 6 pops the leftover 10 T that Pop 1 pushed. It went stale when Pop 2 relaxed T to 8. The duplicate push policy never removes it. The entry just stays in the heap, and when its turn comes, 10 is greater than dist at T, which is 8, so it is dropped without touching any vertex. Pop 7 and 8 are the same pattern for X. 2 old copies from earlier, weaker relaxations, 14 from Pop 2 and 13 from Pop 3, both beaten by Pop 4's dist at X of 9. And the final answer matches the trace exactly. S0, T8, X9, Y5, Z7. Here is the rule in one place. Duplicate push Dijkstra never deletes an old heap entry when a better one is pushed. It just leaves both in the heap. The old entry is caught on pop by comparing the pop distance against dist at U, not by checking a separate, already finalized array. A vertex can sit in the queue under several different distances at once. Only the smallest one ever does real work, and every larger copy is skipped when its turn comes. Prim's frontier has exactly the same shape. A key and vertex pair is pushed whenever an edge lowers a vertex's key. On pop, Prim skips a vertex already in the tree, using its in-tree marker, the inMSD array. So there is no decrease key. The one difference from Dijkstra is that Prim keeps this separate in-tree marker, while Dijkstra reuses its distance array. This C maps one-to-one onto the pseudocode. The function takes the adjacency list, the source, and the distance array it fills in. First, we set every distance to infinity, our sentinel for not yet reached. Then we set the source's distance to 0. The priority queue is a plain array of entries, with PQN counting how many it holds. And we push the source with distance 0. That is the only seed the algorithm needs. While the queue is not empty, we keep going. We pop the smallest entry off the top, and we read its distance into D and its vertex into U. Here is the stale check. If D is bigger than dist at U, this entry is an old leftover. So we continue and skip it without touching anything. Otherwise we loop over every outgoing edge of U. We read the neighbor V and the edge weight W. Now the relaxation test. If dist at U plus W is less than dist at V, we have found a shorter path into V. So we update dist at V, and we push the improved distance and vertex pair. There is no decrease key anywhere in this function. The cost is big O of V plus E times log V. Each of the roughly V plus E push and pop operations costs big O of log V, because the heap may hold up to big O of E entries. So each heap operation is big O of log E, which is log V for a simple graph. The full program compiles clean under the strict warning flags, and runs clean under the address and undefined behavior sanitizers. To run it, we declare a distance array, called Dijkstra with source 0, then loop over every vertex and print its distance. The output is the shortest distance from S to each vertex. Dist at S is 0, T is 8, X is 9, Y is 5, and Z is 7. These are deterministic values, no raw addresses, which is the Chapter 1 rule, and they match the CLRS worked example for this same graph. Let's meet Prim's algorithm. It builds a minimum spanning tree. That is the cheapest way to connect every vertex using the least total edge weight. Think of wiring every house into the power grid with the least cable. Key at V holds the weight of the cheapest edge that connects V to the tree we have built so far. Parent at V remembers the tree vertex on the other end of that cheapest edge. Each step we pop the smallest key from the frontier, and we add that vertex to the tree. This reuses the same min-heap frontier as Dijkstra, just holding key and vertex pairs. One nice thing, Prim needs only the binary heap from Chapter 12, no disjoints at union, and no forward dependency on a later chapter. Watch out for one belief here. You may think the minimum spanning tree gives you shortest paths too. It does not. An MST connects every vertex at minimum total weight. It is not a shortest path tree. The cheapest way to wire the whole grid can still send you the long way round between two particular houses. Cheapest total is not the same as shortest between any given pair. Let's read Prim in pseudocode. We start by setting every key to infinity and every parent to nil. Then we set key at the root to 0 and push the root into the priority queue. The main loop pulls the smallest key. If that vertex is already in the tree, we skip it because it is an old leftover entry. Otherwise, we add it to the tree. Then we look at every edge leaving the new vertex. If the neighbor is not in the tree and this edge weight W is less than the neighbor's key, we relax it. We lower key at V to W, set parent at V, and push V again. One detail about nil in that pseudocode. Here nil is the C value -1. Stored in parent at V, it is an index sentinel, not a pointer, so it is -1 and not null. That matches Chapter 1's not found convention, -1 for an index, null for a pointer. Your turn to predict. The tree so far is just A, so key at B is 2, key at C is 3, and everything else is infinity. Which vertex joins the tree next and over which edge? And what does adding it change about the remaining keys? Pause the video and predict before you advance. Now the answer. B joins next over edge A to B with weight 2, the cheapest edge crossing out of the tree. Adding B then relaxes C down from 3 to 1, using edge B to C with weight 1. It also sets key at D to 4. Prim always takes the cheapest edge, leaving the current tree. A common trap is picking C because A to C was drawn first, or picking the globally cheapest edge B to C, even though C cannot yet be reached from the tree. Let's trace prim one vertex at a time. We start at A, watch the colors. Green means a vertex is in the tree. Teal means it is in the frontier, so it has a key but is still outside the tree. Red marks the vertex joining this step. Cobalt means we have not reached it yet. Right now A is red, the vertex we start from. On the right is our table. We build it like a teacher at the board. Each added vertex gets one new row and the old rows stay. The key of a vertex is the weight of the cheapest edge that connects it to the tree so far. In the first row, the key of A is 0, and every other key is infinity. A has the smallest key, so we add it to the tree. A turns green. Now we add a new row for A and look at its edges. The edge A to B has weight 2. 2 is less than infinity, so the key of B drops from infinity to 2. B is teal now, which means it is in the frontier. The edge A to C has weight 3, so the key of C drops from infinity to 3. In this row, B is 2 and C is 3. The smallest key outside the tree is B at 2, so we add B to the tree. B turns green and we add the B row. Now we look at B's edges. The edge B to C has weight 1. 1 beats the old 3, so the key of C drops from 3 to 1. The edge B to D has weight 4, so the key of D drops from infinity to 4. In this row, C is 1 and D is 4. The smallest key outside the tree is C at 1. We add C to the tree. C turns green and we add the C row. Now we look at C's edges. The edge C to E has weight 6, so the key of E drops from infinity to 6. The edge C to D has weight 5, but D already has key 4, so D does not change. The smallest key outside the tree is D at 4. We add D to the tree. D turns green and we add the D row. Now we look at D's edges. The edge D to E has weight 2. 2 beats the old 6, so the key of E drops from 6 to 2. That is the only change in this row. Only E is left with key 2. We add E to the tree. Now every vertex is green. The tree is done. The minimum spanning tree uses edge A to B with weight 2, edge B to C with weight 1, edge B to D with weight 4, and edge D to E with weight 2. The total weight is 9. Here is a quick check. Prim runs in big O of V plus E times log V with a binary heap. That is the same bound as Dijkstra. Why? Pause and think. Because the work has the same shape. Each of the V plus E push and pop operations on the frontier costs log V, because the heap can hold up to E entries. Prim uses the same duplicate push and skip hold policy as Dijkstra, so the counting is identical. This is prim in C. It takes the adjacency list, a start vertex, and 2 output arrays, parent and key. In MST, starts all false. This is the array that replaces Dijkstra's stale distance check. Every key starts at infinity. And every parent starts at -1, the index sentinel. We set the start vertex's key to 0 and push it into the priority queue. Compare this with Dijkstra's setup, the same shape with key in place of dist. The main loop runs while the queue is not empty. We pop the smallest entry. Here is the stale check, and note how it differs from Dijkstra's. If U is already in the tree, This is an old leftover copy. So we skip it. Dijkstra compared distances. Prim just asks whether the vertex is already settled. Otherwise, we add U to the tree. Then we scan U's edges. Here is the relaxation, and it is the one real difference from Dijkstra. If the neighbor is not yet in the tree, and this single edge weight W is less than key at V, we have found a cheaper way to connect V. Note we compare W alone, not a running total. That is what makes this a spanning tree and not a shortest path tree. So we lower key at V to W. Record the parent, and push V again with its new key. The cost is big O of V plus E times log V by exactly the same reasoning as Dijkstra. The full program is in the file prim.c. Let's run prim.c and read its output. It prints the 4 tree edges, a to B with weight 2, B to C with weight 1, B to D with weight 4, and D to E with weight 2. The total minimum spanning tree weight is 9. One note: a connected graph gives one tree. On a disconnected graph, this loop reaches only the component that holds the source. The other vertices keep key at infinity, which is how you would spot a second component and restart prim there to build the full forest. Now let's meet Kahn's topological sort. It orders the vertices of a directed graph so every edge points forward. Think of choosing which courses you can take. A course is ready once you have finished every prerequisite. That is exactly in degree 0 in the remaining graph. First, we compute every vertexes in degree once, up front. Then we queue every vertex that already has in degree 0. We remove a vertex from the queue, omit it, and lower the in degree of each neighbor by 1. A neighbor that drops to 0 is now ready, so it joins the queue. One key idea: if the queue empties before every vertex is omitted, the graph has a cycle and no valid order exists. Watch out for one belief. You may think every dependency graph can be ordered, but a topological order only exists for a directed acyclic graph. If Calc 2 needs Calc 1, and Calc 1 somehow needs Calc 2, that cycle can never be put in order. There is no first course. And Kahn's queue does not crash on it. It just stalls, with those vertices stuck above in degree 0. That silence is why the count check at the end matters. Let's read Kahn's algorithm in pseudocode. First, we set the in degree of every vertex to the number of edges entering it. Then we scan all vertices and enqueue everyone whose in degree is 0. The main loop dequeues a vertex U, appends it to the order, and walks its edges. For each edge from U to V, we lower the in degree of V by 1. If the in degree of V reaches 0, we enqueue V at the end. If the order holds fewer than all the vertices, a cycle exists. One note on the queue: it is just a plain array with a head and a tail index. The same first in, first out idea as Chapter 7, and not a new structure. Notice it does not need to be a priority queue. Kahn's does not care which ready vertex it takes next, only that everyone it takes is ready. Your turn to predict. Course 0 intro leads to 1 data structures, then 2 algorithms. Course 3, Calculus 1, leads to 4 Calculus 2. Both 2 and 4 feed into 5 numerical methods. Which courses can you take in the very first term with in degree 0? And after you finish those, which become ready next? Pause the video and predict before you advance. Now the answer. First term, 0 intro and 3 Calculus 1, the only 2 with no prerequisites. Finishing them drops 1 and 4 to in degree 0. So data structures and Calculus 2 open up next. 5 numerical methods waits until both 2 and 4 are done, because it has in degree 2. A common trap is assuming a single linear chain, and missing that 0 and 3 are independent roots that both start ready. Let's trace cons one course at a time. Watch the colors. Green means a course is emitted, so it is done. Teal means it is ready, with in degree 0 sitting in the queue. Red marks the course leaving the queue this step. Cobalt means it is still waiting on a prerequisite. Right now course 0 is teal, and so is course 3. On the right is our table. Each column holds the in degree of one course. In degree just means how many prerequisites a course still needs. Course 0 and course 3 both start at 0, so they are ready. Course 5 starts at 2, because it needs both course 2 and course 4. Course 0 is ready, so we take it out first. Course 0 turns green and we add a new row. Course 0 goes into the output order. Course 0 points to course 1, so we lower the in degree of course 1 by 1 from 1 to 0. Course 1 is ready now, so it turns teal. Next we take out course 3. Course 3 turns green and we add its row. The order is now course 0, then course 3. Course 3 points to course 4. We lower the in degree of course 4 from 1 to 0. Course 4 is ready now, so it turns teal. Now we take out course 1. Course 1 turns green and we add its row. The order is course 0, 3, then 1. Course 1 points to course 2. We lower the in degree of course 2 from 1 to 0. Course 2 is ready now, so it turns teal. Next we take out course 4. Course 4 turns green and we add its row. The order is course 0, 3, 1, then 4. Course 4 points to course 5. We lower the in degree of course 5 from 2 to 1. But 1 is not 0, so course 5 is still waiting. It stays cobalt. Now we take out course 2. Course 2 turns green and we add its row. The order is course 0, 3, 1, 4, then 2. Course 2 also points to course 5. We lower the in degree of course 5 from 1 to 0. Course 5 is finally ready, so it turns teal. Only course 5 is left. We take it out. Now every course is green. Read the final order across. It is course 0, 3, 1, 4, 2, and 5. All 6 courses came out, so the graph has no cycle. Here is a quick check. Suppose you run Kahn's algorithm on a graph that contains a cycle. What happens to the queue? Pause and think. Here is the answer. The vertices inside the cycle never reach in degree 0, because each one is still waiting on another vertex in the cycle. So the queue empties while some vertices are still unemitted. And that is exactly the cycle detection signal. The length of the order is less than the number of vertices. This is Kahn's algorithm. In C first we scan every vertex, and in Q the ones whose in degree is already 0, seeding the queue with all the roots. The while loop dequeues U, appends it to the order, and walks its edges. For each edge, we decrease the in degree of the target by 1, then check if it is now 0. The moment it reaches 0, we enqueue that vertex. We return count, the number of vertices emitted. The cost is big O of V plus E. Every vertex is dequeued at most once, and every edge is examined at most once, to decrement its target's in degree. Notice there is no log factor here, because there is no heap. Kahn's is the cheapest of the 3 algorithms in this chapter. The full program is in kahntopo.c. One note on bounds. Production code checks every array bound before writing. Here, Q at tail++ relies on tail being less than V, and a fixed V-sized Q always satisfies that, because each vertex is enqueued at most once. Let's run kahntopo.c. It prints the topological order 0, 3, 1, 4, 2, 5. This is one valid order among several. The initial ready roots are in queued and increasing index order, and after that the plain first in, first out queue fixes the order. So the result is the same on every run. Let's compare 4 more classic algorithms. We name them and their trade-offs, but we do not reimplement them here. Kruskal also builds a minimum spanning tree. It sorts all edges and adds each one if it does not create a cycle. We do not build it here because it needs a disjoint set union structure, which comes in Chapter 19. Bellman-Ford finds shortest paths. It relaxes every edge, v-1 times. It handles negative weights, but it costs big O of v times e, so it is a comparison only here. Floyd-Warshall solves all pairs' shortest paths using dynamic programming over intermediate vertices. We only compare it here because it is big O of v cubed and it is a different problem shape. All pairs, not one source. And there is a second way to do a topological sort. Run DFS to completion, then reverse the finish time order. That one reuses Chapter 15's DFS as is, so Kahn's is the runnable main example here instead. One scope note. Kruskal is not a runnable example in this chapter. It needs a disjoint set union structure this course has not taught yet, which is Chapter 19. Treat it as a trade-off mention now, and its full implementation as a later challenge.